Chiji, Bismillahirrahmanirrahim. First of all, we will discuss that what are the sluice gates, and what is the use of the sluice gates. In this image, you can see that there is an open channel on which there is a weir, and on the weir is across the width of the channel, and on the weir we can see that there are the gates. These are the gates, 1, 2, 3, 4, and so on. You can see number of gates on weir across the channel. These gates are known as the sluice gates. The sluice gates can be constructed on weir across the channel, or sometimes they are installed without the weir. Sometimes it is the combination of the gates and the weir, and sometimes the gates are installed only. The gates are installed across the width of the channel, as you can see in this figure. In this figure, you can see that there is an open channel and there are two sluice gates. One is this gate and the other is this gate. These two gates are installed across the width of the channel, and when the gates are closed, then they meet the bed of the channel. And you can see that there are the mechanical means over here. This is also a bridge on over the gate. This is a bridge. You can walk here, and you can mechanically or automatically you can manage the gates, the opening and closing of the gates. Okay, you can close the gate, you can open the gate. When you need to raise the level of water, then you close the gate, and when you allow water to flow towards the downstream side, then you open the gate. So the gates are operated mechanically. So these are the sluice gates. What is the function of the sluice gates? Sluice gates are used to raise the level of water at the upstream side. Remember, the function of sluice gate is not to store the water. The storage of water is the function of dams. Okay, and for sluice gates, we say that the function of the sluice gates is to raise the level of water at its upstream side, and that water can be used for different purposes. For example, on the upstream side you have a tributary and you want to divert water towards the irrigation system, so you need to raise the level of water at the upstream side, for which the sluice gates are closed. The water level is raised and the water is diverted towards the irrigation system. Similarly, sluice gates are also used to raise the level of water in order for navigation, for sailing ships, etc. Okay, there can be different kinds of functions. That's why these are known as the control structures. Remember, weirs and venturi flumes are not only the control structures, sluice gates are also the control structures. Here it is written that a sluice gate is traditionally a wood or metal barrier that are set in the sides of the waterway. They are used to control water levels and the flow rate. They are used to control the water levels, means they are used to raise the level of water, and when you do not need to raise the level of water, then the gates are open to allow water to flow towards the downstream side. They are also used to control the discharge. If you see that there is a high discharge at the upstream side, there is a condition of flooding, or a high discharge may cause sedimentation, etc., then you can open the sluice gates and you will allow extra discharge to flow towards the downstream side. This is how you can control the discharge. Okay, it is used to control water level and discharge in rivers and canals under ideal conditions where friction is ignored. Remember, the sluice gates are, when constructed, it is the engineers make sure that the bed of the channel at the upstream side and at the downstream are lined enough to control the friction. There is no friction. We can't say that there is zero friction, but for a good lining, we can assume that there is no friction, and thus we say that the energy is conserved, means the energy remains constant. The energy of flow at the upstream side is equal to energy of flow at the downstream side. There is no friction because of the good lining, and this is our assumption, which is quite good assumption, acceptable assumption. Okay, so these are all about the sluice gates, and now we go towards our lecture. Okay, remember that this is someone was asking me about the recommended book and its edition. Here you can see that this is the recommended book, Fluid Mechanics with Engineering Application, SI Metric edition, and these are the three authors. So all of you must have this book for the assignment. Okay, Jim. First of all, in today's lecture, we will discuss about what is the discharge curve and what are the components of the discharge curve. You can see that there is a figure. This is a side view of the broad crested weir that is installed across the width of the channel, and you can see that this is a movable sluice gate. You can open the gate, you can close the gate. When you will close it, it will join the broad crested weir and it will raise the water off level on the upstream side, and when you will open the gate, it will allow water to flow towards the downstream side. You can see this is the upstream side and this is the downstream side of the channel. Okay, first of all, when the gate is closed, you can see that this is the level of water. Okay, and for this level of water, you can see that the velocity head is very small, because the water will be static, almost in static condition here, or you will say that the velocity, approaching velocity, will be zero. So you can see that we have the high depth of flow, that is why one is very large as compared to the velocity head. Or in terms of energy, you can say that here, when the gate is closed, the potential energy of flow is very high as compared to its kinetic energy at the upstream side. Now what happens when the gate is open? You can see that this is the opening of the gate. When the gate is open, then the water starts flowing towards the downstream side beneath the gate. So just behind the gate, you can see that this is the depth of the flow, which is actually the critical depth of the flow, and here we have the critical velocity head. At the downstream side, the depth of the flow is very small, but you can see that we have enough velocity head. At the downstream side, the velocity will be high. But in all the cases, you can see that the energy line remains constant. This is what we discussed earlier, that there is no, we assume that there is no friction, or friction is ignored, and we assume that the energy is conserved. That is, the energy line remains constant. So the energy line remains constant, and this is what we have situation. Just before the gate, when the gate is opening, we have the critical depth of the flow and we have the critical velocity head. What the figure shows side view of a flow over broad crested weir, and it also shows the variation of the depth of the flow and discharge for a constant specific energy. Remember that we have the constant specific energy, that is, the energy line remains constant, and we can see that we have different depths of the flow, and thus we have different discharges. Okay, with the variation of the depth of the flow, the discharge also changes. Okay, now in order to develop a discharge curve, we see this equation which we have already discussed in our previous lecture, that specific energy head is equal to y plus square of v divided by 2g, and we know that this v, this is the relationship between this v and the unit discharge is this: q is equal to v into y for rectangular channels. So we are going to develop this equation for and this discharge curve for the rectangular channel. So we can put the value of v from this equation in this equation, and we will get this simplified equation: y plus square of q divided by 2g into square of y. And by simplifying this equation, in the end we get this result for the unit discharge. Okay, we already discussed that the energy is constant. So if you take this energy as constant, and we know that 2g is a constant term, so taking energy as constant, you can put different values of y in this equation, and you can get different values of the unit discharge, and you can develop a relationship between the unit discharge and the depth of the flow, and then we will construct a discharge curve. You can simply use this equation also. It is up to you. You can put the values of E and Y in this equation, and you can get different values of Q, or you can put the values in this simplified equation, and you can have different values for the unit discharge. Okay, let's see how can we develop the relationship. You can see here that this is the actual relationship, actual equation. E is equal to y plus square of q divided by 2g into square of y, and this is the simplified form for the q. Q is equal to under root of 2gy square into e minus y, which we have developed already. Okay, this time I have worked on the FPS system. Let's suppose that specific energy head is 5 feet. And what is 2g? We know that g is equal to acceleration due to gravity is 32.2. So multiplied it with 2, we will get 64.4 feet per square second. Okay, now we will put this value of E and 2g in this equation, and we will, for different values of y, we will get different values for the unit discharge. Here you can see that I have taken different values of y from 0 up to 5 feet. You can see that the values are from 0 up to 5 feet, and putting these different values of y in this equation, I have got these different values. And on the basis of these two values, I have got a discharge curve. Here you can see that this is a discharge curve, and this is a relationship between q and y. Sometimes the discharge curve is also known as qy curve. Okay, qy curve. Just as specific energy diagram is sometimes known as EY curve, because that shows the relationship between E and Y. This curve shows the relationship between Q and Y, so it can also be known as a QY curve. Okay, you can see that in this curve, we have again the two limbs. This is the upper limb. Here we have got the maximum value, and then it is again starts to decrease, and we have two limbs. This is the upper limb, and this is the lower limb. Let's discuss the components of the discharge curve. In this figure, you can see that we have a discharge curve. This blue line shows you the discharge curve, which is for the constant specific energy head. Okay, now we can see that in this curve, here we have the maximum discharge. On x-axis, this is the maximum value, which is almost about 34. Okay, so this is the maximum discharge we have. And what was the reason? In case of the sluice gates, you can see in start, when the gate is closed, then we have the high depth of flow and the discharge is almost zero. So this shows you the same situation. You can see here that we, at this point, we have the maximum depth of the flow, and you can see that the discharge is zero at this condition. Now when you open the gate, what happens? The depth of the flow starts decreasing and the discharge starts to increase. At this point, you get the maximum discharge, and then it flows towards the downstream side, where you can see the depth of the flow starts to decrease, and the discharge also starts to decrease. So we get this type of the curve where we have the maximum discharge at this point. And remember that corresponding to this maximum discharge, we have the depth of the flow, which is known as the critical depth of the flow. This is the only point on the curve where we have the single depth of the flow. Except this point, on every other point, or you can say that except this value of the maximum discharge, which is also known as the critical discharge. Why? Because it is corresponding to the critical depth of the flow. So remember that corresponding to critical depth of the flow, we have always the maximum discharge, which is also known as the critical discharge. Except this critical discharge or maximum discharge, for all other value of unit discharges, you will get two depths of the flow. For example, if I take this value Q1 dash, that is equal to 25, then you can see if I extend a line from this, it will touch the lower limb and then it will touch the upper limb. From upper limb, you can extend line towards the y-axis and you will get the depth of the flow y1 dash. From the lower limb, you will extend line towards the y-axis and you will get the depth of the flow, that is y2 dash. So these are known as the alternate depths of the flow because one of the depth of the flow is in the subcritical state and other is in the supercritical state. You can see that this is the critical depth, and we know that the depth of flow above the critical depth is a subcritical state, and this is the region where the depth of the flow is smaller than the critical depth of the flow. So this is a supercritical state or supercritical region of the flow. And this curve shows you that for every value of the unit discharge, you have two depths of the flow, y1 dash, y2 dash, one of which is in the subcritical state and other is in the supercritical state. Similarly, there is another example. For example, the unit discharge is 10 Q6 per feet. So you can see that when I extend a line from this discharge curve, it touches the lower limb and then it touches the upper limb. For upper limb, you will get the depth of the flow y1 double dash, and from the lower limb, you will get the depth of the flow, that is y1 double dash. Again, one of them is in the subcritical state and other is in the supercritical state, and both gives you the same discharge. Okay, so from this discharge curve we have come to know about that there is only this point where we have the single depth of the flow, and that single depth of the flow is known as the critical depth of the flow, except this point on except this value for the maximum unit discharge. For all other discharges, you will always get two depths of the flow, which are known as the alternate depths of the flow. Remember that this discharge curve is on the basis of the constant specific energy. So now we can discuss that what are the components of the discharge curve. These are the components of the discharge curve. Number one is critical depth. Critical depth is the depth of flow corresponding to maximum discharge for a given specific energy. You can define critical depth on the basis of the discharge curve, or you can define it on the basis of the specific energy diagram, which we discussed in our previous class. Whenever you are asked to define the critical depth, it is up to you whether you want to define it on the basis of the specific energy diagram or you want to define it on the basis of the discharge curve. It is up to you. Both the definitions are accurate. In case of the specific energy diagram, we discussed that critical depth is the depth of flow where specific energy is minimum for the constant unit discharge. And here we say that critical depth is the depth of flow where the unit discharge is maximum for a constant specific energy. You must have to say that which term is constant. For specific energy, unit discharge is constant, and for discharge curve, specific energy is constant. Thus, we can also define critical flow as the flow at which discharge is maximum for a given specific energy. and these are the alternate depths. You can also define the alternate depths on the basis of the specific energy diagram. Here we say that for a given specific energy, or you can say that for a constant specific energy, the depths of flow corresponding to a given discharge are known as alternate depths of the flow. One of them is always in the subcritical state and other in the supercritical state. So it is up to you whether you define the alternate depths on the basis of the specific energy diagram, or you want to define them on the basis of the discharge curve. Is it clear? Is it clear, boys? Are you listening to me?
Yes, ma'am, clear.
Okay. Okay, remember that this was the discharge curve which was developed on the basis of the FPS system, where we had discussed that energy is equal to 5 feet. Energy head is equal to 5 feet, and we took the value of gravity as 32.2 feet per square second. So you have developed this discharge curve for the FPS system, and you can use this curve for the FPS system only. You can't use this curve for the MKS system. If you want to work for the MKS system, you have to develop a graph for that, a curve for that. There is a very easy solution for that. We have a dimensionless discharge curve. As the name indicates, this discharge curve has no dimension on its x-axis and y-axis. You can see that what are the dimensions here? Here, the dimension of the depth of the flow is in feet, and the dimension of the unit discharge is cusics per feet. But in case of dimensionless discharge curve, there will be no unit on the y-axis and no unit on the x-axis, and thus you can use the dimensionless discharge curve for any kind of system unit. Here you can see that we have the same equation, E is equal to y plus square of q divided by 2gy square, and this is from this equation we have got the value of the unit discharge. We have got this value. Again, I have taken the same values, that is specific energy head is equal to 5 feet, 2g is equal to 64.4, and this is the same table I have copied from the previous Excel sheet. You can see this, I have copied this table, this whole table from here on this sheet. Okay, this is the same table. Now what will we do? We will divide this value, these are the values of the unit discharges. Okay, we will divide this value of q by q maximum. You can see q divided by q maximum. So where is the value of the q maximum? First of all, you have to look at the value of the q maximum here. From the figure you can see that here we have the maximum value of the discharge, or from the table if you look, you have this is the maximum value 34.51. You can see that is 34.45, then this is 34.51, and this is again decreasing 34.18. So this is the maximum value 34.51. So I have divided all the values in this column by the maximum value of the unit discharge, and I have got these values. Okay, you can see here the formula B7 divided by 34.51. This is B7, and I have divided it by the value 34.51. That's why I have got the value 1 here, because here 34.51 is divided by 34.51. So I have got the value 1 here. And for all, you can see all the other values are less than 1, because the unit discharge is divided by the maximum discharge. That's why all the values are less than 1, and this is the only value which is equal to 1. So these values are now unitless. Q divided by Q, it gets unitless. Similarly, here I have divided all the values of Y by E. What is E? E is 5 feet. You can see that 0 divided by 5. Okay, I have divided all the values by E. And now you can see that both the values have got unitless. There is no unit. And now I will draw a graph between these two terms, that is Q by Q and Y by V, and that curve will be a dimensionless discharge curve. You can see here I have drawn a dimensionless discharge curve for which on the sorry, for which on the y-axis I have y divided by E, and on the x-axis I have Q divided by Q maximum, or you can say it is Q divided by QC. You can see that the maximum value is 1, which we have already got. This is the maximum value. So this is the maximum value 1. And what is the use of the dimensionless discharge curve? We are going to discuss this. The components are same. If you want to discuss that what are the components of the dimensionless discharge curve, you can see that this is the value of Q by Q maximum, where we have the value equal to 1, and corresponding to this we have the YC divided by E. Corresponding to this unit discharge, we will get the critical discharge for the constant specific energy, YC divided by E. And for all other values of Q by Q maximum, we will get the two depths of the flow, one in the subcritical state and other in the supercritical state. So you can define the components by your own. The components are same as that of the discharge curve. Okay, let's look at here. This is the dimensionless discharge curve. You can see that in this discharge curve, you can see that this discharge curve is again for the constant specific energy. Here Q by Q maximum is 1, and corresponding to this Q by Q maximum, we have got the value okay, just a minute. Okay, you can see that corresponding to this Q by Q maximum, we have got the value. This is actually YC divided by E. The whole y-axis shows you the value of Y by E. It is YC divided by E because it is corresponding to the maximum discharge. Okay, YC is equal to 2 by 3 of E, or you can say YC divided by E is equal to 2 by 3. This is the equation which we developed in our previous class. We discussed that YC by E is equal to 2 by 3 for critical flow in rectangular channels. अगर आपको याद हो तो हमने ये equation develop किया था. और and here you can see that अगर हम इस E को यहाँ पर ले आए तो YC divided by E is equal to 2 by 3, which is about 0.67, and you can see that this is this critical depth of the flow is about 0.67 or 0.7. You can see that this is 0.6, this is 0.8, and YC is somewhere between these two terms. So YC is always equal to 0.6 times specific energy head, or you can say 0.7 times energy head, or you can simply say it is 2 by 3, that is 0.67 of the energy head. Okay, we can see that above this green line, which shows you the critical depth of the flow, we have the subcritical state, and below the green line we have the supercritical state. If we take another value of Q by Q1, yes, here you can see that we have the value. Let's suppose the value of Q by Q1 is 0.8. Now corresponding to this, if we extend a line from 0.8, you can see that it touches the lower limb as well as the upper limb. For upper limb you will get the value Y1 divided by E, and for the lower limb you will get the value Y2 divided by E, and from here you can find the values that one of them will be in the subcritical state and other will be in the supercritical state. Okay, so what is the use of this dimensionless discharge curve? Uh, if we have the values of q divided by q1 in any unit, okay, if now you do not worry about the units. If you have the values for the discharges or specific energy or depth of flow in MKS system or FPS system, don't worry about that. You can use the dimensionless discharge curve. If you have the value of q divided by q1, then you can find the values y2 divided by e and y1 divided by e. And if you have the value of e also, then you can find y1 and y2. That is, you can find the values for the alternate depths of the flow. The other advantage is this. For example, you have the value of y1 and e, means you know one of the alternate depth and the specific energy head, and you are asked to find the value of this y2. You do not have the value of q, both the q's, you do not have the value of q. Then what will you do? It's very simple. You have the value of y1 divided by e, so from y1 divided by e you will draw a line towards the upper limb of the curve, then you will come down to touch the lower limb, and then you will extend your line towards the left side, towards the y-axis, and you will get the value of y2 divided by e. E is already known to you. E here and here is constant. Why? Because the whole curve is for the constant specific energy head. So if you have also this value of the energy, then you can find the alternate depth of the flow. This will be quite clear when we will solve the numerical problems, because you have to solve them on the basis of the dimensionless discharge curve, and you will come to know it clearly. Is it clear?
यस मैम क्लियर है.
ओके, मुझे एक चीज देखने दे. Q डिवाइडेड बाय Q मैक्सिमम. ओके, here you can see that what is the importance or use of the dimensionless discharge curve. We already discussed that if we know the value of E and Q maximum, we can find the value of Q for any given depth of the flow. और जो भी हमने discuss किया था, if E and one of the alternate depth, for example, if E and Y1 is known to you, then you can find the value of Y2, or if E and Y2 is known to you, then you can find the value of y1. And this will be much clear from the numerical problems. So let's solve the numerical problems. Okay, first of all, we have a problem number 36. I am opening my book. ये मैंने आप लोगों के लिए स्कैन किए, but the book is tightly binded, so the scan is not quite clear. You can open your Fradini books. It is page number 394. Problem number 36. It is written that water flows with a velocity of 1.2 meter per second and a depth of 0.6 meter in a wide rectangular channel. Is the flow subcritical or supercritical? Depth of the flow is given, velocity of the flow is given, and it is also given that this is a wide rectangular channel. We know that the wide rectangular channel is one where the depth of the flow is very, very small as compared to the width of the flow. We have to find the state of the flow, whether it is subcritical or supercritical. And number two, we have to find the alternate depth for the same discharge and specific energy by two methods. Number one, by direct solution, and number two, by use of the figure. The figure is actually the dimensionless discharge curve. So we have to find the alternate depth by the discharge curve and by the equation. So this is the data for the problem number 36. Velocity is given, depth of the flow is given. We have to find the type of the flow, whether it is subcritical or supercritical, and we have to find the alternate depth by direct solution. And by direct solution means by using the equation and by use of the figure 11.12. If you check figure number 11.12 in your Franzini book, it is actually a dimensionless discharge curve. So first of all, we will find the type of the flow. For type of the flow, we have two methods. Number one method is to find the critical depth of the flow. Once we find the critical depth of the flow, then we can compare this given depth of flow with the critical depth of the flow. If we found that this given depth of the flow is greater than the critical depth of the flow, then the flow will be subcritical, otherwise it will be supercritical. And second method is to find the Froude number. If you find the Froude number and the Froude number is less than 1, then the flow will be subcritical. If the Froude number is greater than 1, then it will be supercritical. So you have two methods to find the type of the flow. You can find it by comparing with the depth, critical depth of the flow, or you can find it by finding the Froude number. So first of all, this is first method, finding yc and compare it with the given value of y. If y is greater than yc, it will be a subcritical state. If y is less than yc, then it will be a supercritical state. So how can you find the value of yc? First of all, Q, we will find the value of the unit discharge for the given data. V is given 1.2, Y is given 0.6. So this is 0.72. It is also given in this question that energy and discharge remains constant. Means once you find the value of energy and discharge for the given data, then you can use it for the whole solution, because that value will be constant. So now we can see that here we have developed this equation in our previous lecture, that square of Q is equal to G into cube of YC. So from here you can find the value of YC, that is equal to 0.375. And what was, this is about 0.4. And what was the given value? The given value was 0.6. Since 0.6, this value of depth of the flow is greater than this value of the critical depth of the flow, so we will say that the given depth of the flow is actually in a subcritical state. You can see here that the given y is 0.6 and we have got that yc is equal to 0.375. Since y is greater than yc, therefore the flow is subcritical flow. Okay, this is the second method for which we find the Froude number, and we know that if Froude number is equal to 1, the flow will be critical. If it is greater than 1, then supercritical, and if it is less than 1, then it will be a subcritical flow. Here we have a formula for the critical flow, for the Froude number. Froude number is equal to V divided by under root of Gy. Putting the values, we will get the value equal to 0.49. Since it is less than 1, therefore the flow is subcritical. I will recommend all of you to find the Froude number whenever it is asked you to find the state of the flow. It is very simple. Your calculations get simple. You have to use just one formula. Whether it is up to you, but I will recommend this method. It is very easy. Whenever, बस आप सिर्फ अपने mind में ये रखें कि whenever you will be asked to find whether the flow is subcritical or supercritical, what will you do? You will find the Froude number, and that will show you whether the given flow is subcritical or supercritical. In our previous class, one of the students asked me a question that this Froude number is equal to Vc divided by under root of Gyc, as we developed it in the previous class. So the answer is this, that we developed this relationship for the critical flow in rectangular channels in the previous class. Okay, this is the general formula of the Froude number. That was the फॉर्मूला ऑफ द फ्रूट नंबर फॉर द क्रिटिकल फ्लो। जब आप यहाँ पे VC और YC लिख लेते हैं ना, तो वो आपके पास क्रिटिकल फ्लो के लिए फॉर्मूला बन जाता है। आपने एक्चुअल फॉर्मूला इज दिस वन। इवन इफ यू पुट द वैल्यू ऑफ V, G and Y here and you get the fruit number equal to 1, then you comes to know this is the critical flow. अच्छा, आपको हो सकता है कि आपको if for example the data is given to you and you are asked to find the state of the flow, it is not necessary that you always get the subcritical flow or supercritical flow. Maybe you put the values in this formula and you get the value of fruit number equal to 1. So what will it shows you? It will show you that the flow is neither subcritical nor supercritical, but the critical one. So this is the general formula to find the fruit number. Okay. The second part of this problem was to find the alternate depth by the direct solution and by the use of the dimensionless discharge curve. So first of all, we will find it by the direct solution. We know that okay, first of all, we will find the value of the specific energy head. I already told you that it is given that the discharge, the unit discharge and the energy will remain constant for this solution. So first of all, we will find the value of the specific energy head for the given data. We know that E is equal to Y plus square of V divided by 2G and V is equal to Q divided by Y. So putting the given value of these terms, we will get the energy is equal to 0.673. Now using this value of energy, we will find the value for the alternate depth of the flow. Okay, again we will use the same equation. Now we are using the same equation for the alternate depth. E is equal to Y plus Q square divided by 2GY square. And here I have tried to simplify the equation. You can see E minus Y into square of Y is equal to Q square divided by 2G. So this is the value for the square of Q. This is the value of 2G. And I have already got the value of E is equal to 0.673. So this is the simplified form of the equation. And if you further make it simplify, you get this cubic equation. Now you can solve this cubic equation by using your calculators, and it will take just a minute or two to solve this equation with the help of the calculator, and you will get three values, that is two positive values and one negative value always. Okay, you have to discard the negative value because the depth of the flow can never be negative. So you have to discard the negative value. So these are the two remaining values. Remember that in these two remaining values, one will always be that value which is in your given data. Okay, it was given that Y is equal to 0.6. One of the depth of the flow was 0.6 and we had to find the other value for the depth of the flow. So the other value is this one, 0.25. This is the alternate depth of the flow. Okay, these are the two depths of the flow, 0.6 in the subcritical state and 0.25 in the supercritical state, which will give you the same value for the unit discharge for a given specific energy. So, and remember, whenever you will solve the cubic equation, you will get the same situation. You will get one of the negative value which you have to discard, and one value you will get which is already given in the data. So you have to choose the third value. Okay. The second method is this, that the given value was 0.6. So you can divide this whole equation number 1 by Y minus 0.6. Okay, we know that Y is equal to 0.6. So you can say Y minus 0.6 is equal to 0. So you can divide this whole equation by Y minus 0.6. Here I have already written that dividing equation 1 by Y minus 0.6, we will get a quadratic equation. And by solving a quadratic equation, you will get two values. Because quadratic equation gives you two values, you will discard the negative value and the remaining value will be the alternate depth of the flow. However, I will recommend you to solve the cubic equation because you can solve it by using your calculator very easily. So this is the best way to solve the cubic equation. I have told you both the methods. You can solve the cubic equation or you can solve the quadratic equation. Okay, this was the method by the direct solution, and now we will find the same value, that is y2 is equal to 0.25, the same value of the alternate depth of the flow by using a dimensionless discharge curve. Okay, you can see that this is the finding the alternate depth by use of the dimensionless discharge curve. Y1 is given, that is 0.6 meter. We have got the value of energy head, that is 0.673. So Y1 divided by E is equal to 0.89, or you can say that it is equal to 0.9. So we will use the value of the dimensionless discharge curve. You can see that this is the dimensionless discharge curve. Okay, and you can see that this is 0.8 and this is 1. So between 0.8 and 1, this is actually 0.9. Okay, this is 0.9. So I have written here that y1 divided by E is equal to 0.9. We don't need to find the value of Q. Just from this value of 0.9, we will move towards the curve like this. Then we will come towards the lower limb of the curve, and then we will move towards the right side, and we will get that y2 by E is equal to 0.4. You can see here that here y2 by E is equal to 0.4. So what will be the value of y2? We will multiply this value of 4 by E. E is 0.673, and so we will get the same value, that is 0.25. So with the help of dimensionless discharge curve, we have got the value of the alternate depth of the flow very easily. But you must know about the direct solution, that is the use of the equation also, because dimensionless discharge curve may or may not be available to you, especially if you are in your examination hall. So it is not easy job to draw the dimensionless discharge curve at that time just to find the alternate depth of the flow. So I will recommend that you must know both the methods, but if we compare, then dimensionless discharge curve is quite a simple method. There is no extra calculations, and you can easily get the value for the depth of the flow. Okay, ji. Now this is problem number 37. For problem number 37, just look at the problem statement. It is given that water flows down a wide rectangular channel of concrete for which meaning roughness coefficient is given, that is N is equal to 0.014, laid on a slope of 0.002. Find the depth and the rate of flow for critical condition in this channel. Okay, it is already given that the flow is critical in the channel. So we have to find the depth and the rate of the flow, means we have to find the critical depth of the flow and the critical discharge. Slope is also given and meaning roughness coefficient is also given. So this is given. We have a wide rectangular channel for which this is the width of the flow, this is the depth of the flow, and meaning roughness coefficient is given 0.014. Slope of the channel bed is given 0.002. This is the critical depth of the flow, and we have to find the critical depth of the flow, and we have to find the critical unit discharge, which is actually the maximum discharge. Okay, first of all, you must know that for a wide rectangular channel, we already discussed that for a wide rectangular channel, the depth of the flow is very, very small as compared to the width of the flow. So what is the area for the flow in a wide rectangular channel? Area is equal to B into Y, and wetted perimeter is B plus Y. That is B plus 2Y. Here we can say that this term is equal to 0 because depth of the flow is very small, so we can ignore it. A very small value when adding to any term will not ignore it. So here we will say that this term is equal to 0 because it is getting multiplied by the width of the flow here. However, you can ignore this value while finding the wetted perimeter because it is getting add to the width of the flow. So here we will say that this value is equal to almost equal to 0. So wetted perimeter is equal to B. Hydraulic radius is equal to area by wetted perimeter, putting the values. Area is equal to B plus Y, and wetted perimeter is equal to B. Cancellation of B on the cancellation of B, and we will get the value hydraulic radius is equal to depth of the flow. So there is no need to learn or do all these calculations for the wide rectangular channel. You must know that for wide rectangular channel, hydraulic radius is equal to depth of the flow. Whenever you get the numerical problem for a wide rectangular channel, you must know that its hydraulic radius is equal to the depth of the flow only. Okay, and this is what we are going to do in this numerical problem. First of all, we have to find the critical depth of the flow. For critical depth of the flow, we are going to use the meaning equation for velocity, that is velocity is equal to 1 by n r power 2 by 3 s naught power 1 by 2. And we know that for critical flow in a rectangular channel, Vc is equal to under root of gyc. This is the equation. This is the equation which we developed in our previous lecture. So we will put here Vc is equal to under root of gyc, and then we will simplify the equation, and putting all the values we will get the value for the critical discharge, that is 0.88 meter. So this is the answer of our first question. What is the critical depth of the flow? The critical depth of the flow is 0.88 meter. The next is to find the critical discharge. For critical discharge, we have two formulas. QC is equal to VC into YC. YC is now known to you, that is 0.88. And for VC, if you want to find the velocity value of velocity, you can again use the meaning equation. Okay, in this meaning equation, just put the values. Now there is no need to use this term gyc. Just put the value in this term. N is known to you, hydraulic radius is equal to yc is now known to you, slope of the channel bed is given to you, so you can find the value of the velocity, and you can use this equation to find the critical or the maximum discharge. This is the second method. We have this equation also, q square c is equal to g into cube of yc. So you putting values in this equation, you can get the value for the critical discharge, that is 2.61 cubic meter per second per meter. You can see method number 2 is simple as compared to method number 1. So it is up to you, but I will recommend this method. You have to learn all the formulas. Sometimes the student want to use the simplest formula, but they do not remember what the exact formula is. They get confused sometimes. So you must know about all the formulas. If you are confused in one formula, you can use the other formula, and thus you can solve the numerical problem. Okay, problem number 38. In problem number 38, it is given that water is released from a sluice gate in a rectangular channel 1.5 meter wide, such that the depth is 0.6 meter and the velocity is 4.5 meter per second. Number 1. Number 2, the critical depth for this rate of discharge. Number 3, type of the flow, and alternate depth by either direct solution or the dimensionless discharge curve. Okay. There are a lot of things to find in this problem. Yes, this is the solution. You can see that this is given. We have given that there is a wide rectangular channel for which the width of the flow is 1.5 meter, depth of the flow is 0.6 meter, velocity is 4.5 meter per second. What we have to find, we have to find yc for a given energy. Okay, for a given data, we will find the specific energy, and for that value of specific energy, we will get the value of yc. Then we have to find yc for a given discharge. For a given data, we will find the discharge, and then we will find the value of yc. For that, we have to find the type of the flow, whether it is subcritical, supercritical, and we have to find the alternate depth of the flow by direct solution or by using the dimensionless discharge curve. Okay, first of all, we have to find the value of yc for a given specific energy head. So first of all, I will find the specific energy head. Specific energy head is equal to y plus square of v divided by 2g. Putting the values, we will get this value 1.63 meters. Now we have to find the value of yc. We know that energy is equal to 3 by 2 into yc. So from here we have got this value of yc, 1.09 meter. So for this specific energy, we have this critical depth of the flow. Next, we will find the value of yc for a given discharge. So first of all, we will find the unit discharge. Unit discharge is equal to V into Y. V is 4.5, Y is 0.6. So we have got this value, 2.7 cubic meter per second per meter. And now we will put the value of Q in this equation. Square of Q is equal to G into cube of YC. And from here, we will get the value of YC, that is equal to 0.906 meter. Next, we have to find the type of the flow, for which we will find the Froude number. You can see that the Froude number is equal to V divided by under root of GY. So putting the given values, we get it equal to 1.85. Since Froude number is greater than 1, therefore this is a supercritical flow. Okay, now we will find the alternate depth of the flow. Okay, remember, now you will find the alternate depth of the flow, and since this, the given depth of the flow, what was the given depth of the flow? 0.6 was the given depth of the flow. And we have got that this is in the supercritical state. It means that now we will find the subcritical flow. We will find the alternate depth, that is the flow in the depth of the flow in the subcritical state. So it must be greater than 0.6. This is your check if you are getting any error in your calculation or not. Remember that if you find that the given depth of the flow is in the subcritical state, then you must know that you are going to find the alternate depth of the flow that will be less than the given value, the given depth of the flow. Here we have got that the value is 0.6, which is in the supercritical state. So we will get the value, the alternate depth of the flow, that will be greater than 0.6 because it will be in the subcritical state. So let's find the value of the depth of the flow. Here you can see that E is equal to y plus square of v divided by 2g, or it is square of q divided by 2g y square. And I have put the values here, and you can see that I have simplified. Now I have got a cubic equation here. Okay, you will solve the cubic equation and you will get the value of y here, and you have to do this by yourself, and you will tell me in the next week in our next lecture that what was the value of the depth of the flow. You have to solve this cubic equation, but remember that the value of y you will get must be greater than the given depth of the flow, that is 0.6 meter. Okay, you can solve this cubic equation, or you can use the dimensionless discharge curve. It is up to you, but you have to tell me the value for the depth of the flow in our next class, inshallah. Okay, this is the last numerical problem. This is not from your Franzini book. You can see the statement: water flows in a rectangular channel that contains a sluice gate. The sluice gate is provided in a channel. The upstream depth of the flow is 5 feet and the sluice gate opening is 1 feet. And the unit discharge is 10 square feet per second. What is the flow depth at the downstream of the gate? You can see that this is an open channel. You can see that this is the bed of the slope, this is the sluice gate, and the depth of the flow at the upstream side is 5 feet. This is the opening of the gate, that is 1 feet is the opening of the gate, and we have to find the value of y2 here. This is the given unit discharge, that is constant, 10 square feet per second. We have to find the value of y2. So how can you find the value of y2? First of all, we will find the energy, because we know that for the sluice gates, the energy remains constant. So this is for the constant specific energy. First of all, you will find the value of the energy for the given data, that is y1 plus q square divided by 2gy square, and that is equal to 5.06 feet. Now you will put this value again in the given equation, that is E2 is equal to Y2 plus square of Q divided by 2GY square. By simplify again, you will get the cubic equation. When you will solve the cubic equation, you will get this value, that is 0.59 feet. Again, you can solve the cubic equation, or you can use the dimensionless discharge curve, or you can use the quadratic equation. There's also a method you can find the value of y2 by trial and error procedure also, but that will be a quite lengthy procedure. Okay, so I will recommend you to solve the cubic equation. Yes. There is also a hint: if you want to solve it by trial and error procedure, you can see that in the subcritical state, the depth of the flow is 5 feet, and now we are going to find the depth of the flow in the supercritical state as shown in the figure. So if you want to do trial and error procedure, you can see that the depth of the flow at the upstream is 5 feet. So you will put different values of y2 that should be less than 5. Try all the values less than 5, and then you will get this value of 0.59 feet. You will not try the value equal to 5 or greater than 5, because it will again be in the subcritical state. You have to try the values in the supercritical state. Is it clear to you, boys? Okay, in the end, this is not your assignment, but you have to solve the problem number 39, 40 and 43 also. ठीक है, इसको try कर लें. If you get any problem, we can discuss it in the next class. One important thing is also, आप लोगों ने in I don't remember that what was that numerical problem, but in one of the problem it was stated that there is wavy flow in a channel. Remember that whenever the flow is wavy in a channel, it shows you that the flow is a critical flow. Okay, we already discussed that on the critical slope, the flow is uniform but unstable. Unstable means it is in wavy form. Okay, so whenever you get that the flow in a channel is wavy, you must know that the flow is a critical flow. So that was all about our today's class. Now,
Ma'am?